Thanks for being here. We're going to go ahead and get started with the program. Some people may continue to eat, but that's okay. We're a social group, and there's no problem with that. Before I turn the microphone over to Lee, I wanted to make one other announcement, which has to do with your club's generosity with regard to the Northern Virginia FM Association, NVFMA. Who here has never worked 2-meter FM through any of the FMA repeaters, 9.1, 7.9? You never done that? You've never done that? Oh man, we got to fix that problem. You've never, come on. You have never. You serious? Okay, we'll fix that. Anyhow, the vast majority of the club knows that without the NVFMA, the repeater coverage in this area will be limited to our repeater, which is one day going to be better, but it's still pretty narrow in terms of the footprint. So we donated some money to the NVFMA, and they're very, very grateful. And thank you for your generosity. Okay, going to turn the microphone over to Lee, who's going to teach us about the history of sideband and other forms of modulation. You're going to learn stuff tonight that you never even knew existed, including Maxwell's equations. Thank you.
No. I don't think we hit the Maxwell's. Okay, so our focus is on modulation with SSB and how we generate SSB. So let's get going here. Some real basics. When we use radio, we want to communicate. We want to send information. Okay, so we have to modulate the carrier. The carrier doesn't provide any information. It's a signal that's there. So technically, they usually break down modulation in the following three categories, and this is the way the emission designators for the ITU are set up. One is we vary the amplitude of our signal, and we actually vary a lot more than that, but we'll get to that. We vary the angle, or we can pulse modulate the signal, and there's things that are used for pulse width modulation, pulse position modulation that convey information based on the timing of your pulses. But we're not going to get into that. But one point is important, is all modulation requires bandwidth. Bandwidth is a very overused term these days. But reality is that bandwidth literally means for us what it really is. It's the width of spectrum required to convey the intelligence we want to communicate. And also, when we look at signals, we can look at them in two ways. We look at things in time domain or the frequency domain. So you're looking at a oscilloscope, you're looking at a signal in the time domain, how it varies with time. If I go to a spectrum analyzer, I can see how the signal looks in terms of the realization of the frequency. And you can actually mathematically transform between the two using something called a Fourier transform that was invented back in the 1700s. So let's talk a little bit about angle modulation real quick. Just going to touch on this. Frequency modulation, phase modulation are very similar. One term to know is the deviation, which is the extent to which the frequency change varies relative to the carrier frequency. And the difference between frequency modulation and phase modulation, okay? Frequency modulation, the instantaneous deviation of the signal, how far it's moving off, is proportional to the instantaneous amplitude of our modulating signal. And of course, since the signal is varying in frequency, the deviation is varying in frequency as well. Phase modulation is a little bit different. It's really the derivative of the signal. So it's proportional to the rate of change in the amplitude of the signal. So this is the difference. One is the actual amplitude, the other is the rate of change in the amplitude, is phase modulation. So there's an interesting thing that happens technically. If I take a FM transmitter and I run the audio through a 60 dB per octave pre-emphasis network, that is, it accentuates the high frequencies, the output will look identical to a phase modulation transmitter. And receiving, the same thing happens in reverse. If I have an FM signal and I do a de-emphasis, it'll look like the same as I'm receiving a phase modulated signal. So the really weird thing is, for us, most of our FM radios have pre-emphasis, and they have de-emphasis in the receiver. So we really aren't transmitting FM, we're really transmitting phase modulation. So just an interesting note. So let's go on to AM, which is really what I want to talk about. So what AM is really in the time domain, if you will. It's a multiplication of the carrier signal by our modulation. Mathematically, it's multiplication. So when I come to CW keying, think of your string dish dots and das and dits as a sequence of 1 and 0s. And you actually apply this binary sequence to turn the RF off and on for various lengths of time. So we're actually, quote, amplitude modulating the signal a little bit. However, what we're really doing is more than just generating a varying carrier level, okay? The multiplication process generates additional frequencies around the carrier, which is, of course, part of what gives us bandwidth. It takes up more spectrum space than just the carrier does. And in any kind of pulse modulation, which is in essence what we're doing here at CW, since we're turning the transmitter off and on, we generate a bunch of spectral lines in frequency that are offset from the carrier. And I'll show you a picture of this in just a minute. But basically, the distance these lines are from the carrier, and there's lines in all their harmonics, so they go out for quite a while, is a function of the keying rate, okay? The faster you send, the more spacing there is, therefore the more bandwidth they take, okay? Now the amplitude of those roll-off energy, these signals that we're generating, is a function of the width of our modulating pulse, how long your dit or da is, and it's actually also very much influenced by the shape of the waveform, and I think that's the important thing we want to get to here in our discussion. So I'm going to transmit a series of dits at 20 words a minute, okay? Approximately 60 milliseconds on time at a rate of 120 milliseconds. It's just my little picture up here at the red arrow showing you the 120 milliseconds, and my dit's about 60. So what we get out of that is a whole bunch of lines that are 8 hertz away from the carrier, because the inverse of our 120 is 8 hertz. 120 milliseconds is 8 hertz. So what we really have coming out of the transmitter is a whole bunch. We have our carrier signal going off and on, but we also have a whole bunch of these spectral lines that are spaced 8 hertz and multiples of 8 hertz away from our carrier. Okay? Now, as I mentioned, the shape of the bandwidth that takes kind of depends on how wide that pulse is and what our shape looks like. So I took 3 cases here. The red lines you see is I transmitted a pulse that has very poor or very sharp rise and fall times. In this case, it was 10 microseconds. So this is kind of like what would happen when you plugged your key into and did a cathode keying on your DX40 or your homebrew radio and didn't really have a waveform shaping circuit. So you end up with a spectrum that looks very broad. This is plus or minus 500 hertz here. So I increased the rise time and fall time to about 1 millisecond to make it a little bit more rounder. And that's my blue one. And then I went really rounded off the pulse by changing my rise and fall time to 10 milliseconds for my pulse that is running only 60 milliseconds. So I'm really rounding the pulse off. But look what's happened to my spectrum here. And see how much it's decreasing. And by the way, one interesting special thing with this, if I actually transmit an exact square wave, so my, the off and on times are absolutely identical, all the even order harmonics would disappear, and the only thing I would have left would be all the odd order ones. So that's kind of a interesting aspect of physics. So I'm going to look over a little bit wider bandwidth. This time we're looking over plus or minus 5 kilohertz. And you can see a dramatic difference. And this is why people used to get pink tickets from the official observers with their transmitters that didn't have a very sophisticated keying circuit and didn't really do waveform shaping. Because if you'll notice here, 5 kilohertz away, it's like 60 dB down. Yet at a kilohertz away, we're only about 45 dB down with our rather crude directly keyed cathode. Whereas on my shape keying waveform here, you can see we're way much further down. So what this shows you is why it's very important in transmitter designs and your homebrew rig to shape that CW pulse. And probably the optimum design would be of something called a cosine square shape. And that would have the cleanest emission spectrum. So let's move on to AM, which is the basics of single sideband. It's basically an AM type signal. So again, AM is a multiplication of the RF carrier with the applied modulating signal. Okay, so one thing important about AM, and we'll get into this a little bit more too, the RF carrier is affected by the modulation. It does not carry any information. Okay? All the intelligence is in the 2 sidebands you generate. However, the carrier does do a good thing for us for our conventional AM broadcast stations, and that is if you're using a simple diode detector, so-called envelope detectors, it provides the reference signal to allow those to demodulate the signal and recover the modulation waveform. So that's the one thing that the carrier does do for us. But the problem is it makes the AM very inefficient, and we'll get into the numbers here in the next slide. So there are some schemes that try to improve the efficiency. One is called control carrier AM, and what they do there is they actually change the amplitude of the carrier depending on the amplitude of the sidebands, so to try to get a better efficiency out of the amplifier, out of the transmitter, I guess we could say. So let's see here. Let's look at an AM signal. So my generate AM, as I said, we generate 2 signals. We have our carrier signal, which is constant and unchanging. We have the upper sideband, which is our modulating frequency plus the carrier, okay, with an amplitude depending by the modulation index. That is how hard we're driving it. And then we have our lower sideband, okay? So, you know, it's upper sideband, lower sideband, and I'm using omega because omega is equal to 2 pi times the frequency, and it's just easier to write omega on the slides. It fits better than saying 2 pi f. So we have 3 frequencies coming out of our AM transmitter. As I said, the carrier, the amplitude is constant. We have the lower sideband, and basically the maximum power of that sideband is 6 dB below the carrier. We also have our lower sideband that has a power that's 6 dB below the modulation index. And the information in the 2 sidebands is the same. You'll notice one's the carrier minus the modulation, the other's the carrier plus. We get rid of the carrier, we're just left with our modulation input. Okay? So people will ask me real quick, well, gee, when I look at my output of my AM transmitter, if I'm at a 50% modulation, I have this kind of waveform, and this one I have this. So wait a minute, how do you mean the carrier is not there? There's no signal there when I'm looking at the output of my transmitter on my oscilloscope. Okay. Well, the reason for that is you're really looking here at the total energy. That is both the carrier and the 2 sidebands. So what happens, we're going to explain here in the phasor diagram. So when I generate an AM signal, I generate a lower sideband that's a phasor that's rotating at the rate of the modulation in a clockwise rotation. And remember that because we'll get to that in another part of our presentation at the end. The upper sideband is a phasor rotating clockwise. Okay? I mean counterclockwise, excuse me. So the upper sideband is moving counterclockwise. The lower sideband's moving clockwise. So what happens is as these vectors rotate at the peak modulation here, 100% modulation, all three vectors are in phase and they add up and multiply. So if I have this at a unit 1 and each of these sidebands is unit 0.5 at 100% modulation, at 100% modulation my total amplitude here is a factor of 2. Okay? If I have just a carrier, it would be a factor of 1. When I get to 100% negative modulation, which is the part right here, what happens is the two sidebands are 180 degrees out of phase with the carrier signal. So they sum to 0. So that's why you see the 0 here in your waveform. But reality is that carrier is not changing. It's constant. It's these two sidebands that are moving, and they generate, by adding and subtracting to the carrier, what you see in the amplitude modulation of the carrier. Okay? So there's an issue with this. Let's talk about Mike's net, and he wants to use AM 4 times a year. So we have a conventional AM transmitter, say the old Heathkit DX100 or a Johnson Viking Valiant or whatever. We're running a 100 watt carrier output. At 100% modulation, each of the sidebands has 25 dB watts of average power. However, because when the two are in phase, they sum up to an amplitude of 2, right, which is 6 dB, what happens is our peak envelope power, oops, sorry, hit the wrong button. Our peak envelope power here, back one more, yeah, okay. So our peak envelope power is 400 watts, okay? So the PEP rating on your DX100 running 100% AM modulation, it's putting out 400 watts PEP. 100 watts carrier and the 25 watts in the two sidebands, but again, remember how they have to add in phase. So that's the difference. That's 150 watts average power, but it's 400 watts peak power, peak envelope power. Okay? So, all right. So when we have our Ricebox transceiver, or Yaesu, or Kenwood, whatever, or ICOM, and we get on Mike's net running AM, if we're to run an undistorted waveform, the maximum carrier we can put out is 6 dB below the 100 watts. So basically 25 watts carrier is as much AM power as you can put into a 100 watt PEP rated linear amplifier. And then each sideband will be 6.25 watts. So I guess the moral of that story is if you really want an AM, then run a real AM transmitter. It'll be 6 dB louder for a 100 watt transmitter. Okay? So what about single sideband? Well, single sideband, as we just said, okay, AM, the carrier conveys no information. So we can just get rid of it. Okay, it eats up 2/3 of the average power of our transmitter and conveys no intelligence. Okay, so as we said, it's 6 dB. So as I said, we went through this issue here with the linear amplifier, as I just said. So if I went to a single sideband and only transmit one sideband, power-wise, if I'm limited by the PEP rating of my amplifier, I can get a 9 dB higher level of intelligence sent out compared to an AM signal. So 9 dB is almost a factor of 9.5 or so. I guess we take the anti-log of that. So it's quite a difference, right? Not only that, but also remember that I'm using a single sideband. I'm only training one sideband, so I need to detect one sideband. So my receiver only has to have half the bandwidth, 3 kilohertz. Instead of, say, 6 kilohertz for an AM. So that gives me another 3 dB. So overall, my single sideband has like a 12 dB advantage over an AM system. So I think that's kind of the compelling reason why everybody realized that they need to use single sideband. It actually does. It's the equivalent of having a 1,000 watt linear versus your 100 watt transmitter, okay? And then some. So I'm going to go back. Oops. So what is single sideband? Well, think of it as one way of thinking of it is it's a translation. we're taking our audio signal or whatever we want. It might be FT-8, it might be something else. But basically we're putting it into a single sideband, and we're basically translating it to be either the sum of the carrier or the difference from the carrier. And what we really want is just that sum or difference output and nothing else. And we actually use SSB for just about all our HF activities. All your PSK, AFSK for RTTY. There were days when people directly keyed their oscillators for RTTY. I did with my HT37 in the 1970s. But generally, even most all our digital modes are using single sideband to modulate the transmitters, and some of them even in CW use single sideband. But they do is they inject a keyed 750 hertz tone or 800 hertz tone into the modulator input, and that's their CW signal. So some radios don't do anything but transmit SSB. And SSB is not a new thing. It's been around over 100 years. Okay? 1915, I think, was a turning year. There were three events there. First of all, one of the early engineers at a VLF voice station tuned his antenna circuit and resonant circuits to the lower sideband and tried to reduce the carrier and upper sideband that way. A guy by the name of B.W. Kendall patented the homodyne or product detector, basically a balanced mixer, in 1915. And John R. Carlson of AT&T actually put a patent in for single sideband suppressed carrier modulation, and it was granted in 1923. In 1922, they were using upper sideband at VLF frequencies for transatlantic telephone, using 150 kW transmitter. I'm not sure if that was a rotary spark gap or a... and by 1936, AT&T began using SSB for all their HF long-haul telephone links. So back before World War II, if someone had the money to put a circuit in and get a telephone call from here to England, it was going on single sideband. So this is a copy of the first page of Carsons' patent application for single sideband. And you'll notice here, but these vacuum tubes basically make a balanced mixer. Here's his RF amplifier, his antenna circuit. And the thing to note in terms of how this is a balanced modulator, the RF is fed in parallel to the grids of the two tubes. This little capacitor here, number 8, and the audio is fed in kind of push-pull. So the result is that the carrier cancels out in this output network because you have 180 degrees phase shift in the tubes, but you're feeding them in phase, and it's kind of so you have one going this end of the transformer, the other in this end. So the carriers cancel out in this circuit. And this was the part of the product detector that was patented also in 1915. And Carson went on. Here's the receiver from his patent. You can see here his little RF amplifier. Here's his BFO, this beat frequency oscillator that he's injecting his carrier in to demodulate the carrier, and then a detector, amplifier, and off to his receiver. And he even came up with a kind of a neat tube for his balanced mixer that he had in his patent. You'll notice he had 2 plates and two independent grids in the tube. I don't know if this ever got built, but he patented the idea of having a tube that had the both 2 plates and 2 grids to run a balanced circuit. So, and that was 1915.
For the transmitter.
That was the whole thing.
Not for the modulation type.
Yeah, no, it was modulation. The whole thing. Carson spelled out in his application that there was no information transmitted by the carrier, and the whole
modulation, so that nobody else.
He did.
So that nobody else.
No, he got a patent for AT&T for it. Yeah, Keith.
I'm a little confused. He invented his receiver 8 years before he
No, you can see it. No, you can, the whole thing. It all was in the 1915 patent. Okay? So let's talk about how we generate SSB, which is going to be the focus of our rest of the presentation. So again, we want to take the input waveform, move it to an RF frequency. So basically, if I look in the frequency domain, what I want to do is put in this example. I'll put in my 1 kilohertz audio tone here. I want to put a 9 megahertz carrier in. And I want to get out either a signal at 8.999 for lower sideband or a signal at 9.001 for upper sideband. Okay? So as a practical matter, one could not take an AM signal and probably filter it enough to get rid of the carrier because it's too close to your desired signal. And it's kind of hard to in those days, it was rather hard with the technology they had to even get rid of the unwanted sideband. So a key part of most of our single sideband transmitters is something called a balanced mixer. Okay? And balanced mixers basically are formulated so that we can get the sum and difference frequencies out of the two applied input frequencies. So a single balanced mixer cancels out, in this case it would be like the LO signal, because you'll notice here when it goes through the output, one phase is the windings where it's applied are 180 degrees out of phase with each other. So we couple from the here into here and here, and you notice these two windings are coupled 180 out of phase. So this suppresses the output of the LO into the RF joint. And in theory, what we have coming out of this one is the modulation input plus the sum and difference frequencies, an ideal mixer. Then we have double balanced mixers, which are much more common these days. And basically, they suppress both of the input signals and only provide an output, which is the sum and difference of the two inputs. In the real world, okay, there's always harmonic distortion. And we also have, in the real world, we get low-level undesirables, such as the air modulation, such, for example, you get the carrier plus 2 times the modulating signal as an undesired output. But so part of the goal of circuit designers is how do you build a better radio to provide better rejection of these unwanted signals. So SSB on the filter method. This is what's probably used in most of your radios today. Usually by, in the newer radios, by crystal filters. So it's simple in matter. We have our balanced mixer, right? Take our audio, feed one in into the balanced mixer, or DBM means double balanced mixer, by the way. We feed a local oscillator in. Coming out is the sum and difference, which is what we call a double sideband signal. We have an upper and a lower sideband, no carrier. Then we filter out the unwanted sideband with a crystal filter or mechanical filter or even an LC filter. And then we run through another mixer with a VFO or whatever our signals to take this thing up to our desired frequency. Because this filter is going to be a fixed frequency, right? It's very hard to make this a narrow tunable filter. So, as I said, back in the old days, they actually used LC filters, and this LO was running around 50 kilohertz to get enough to get this kind of bandwidth and rejection. Collins came out in the early 50s with their mechanical filter, which is in all the S-line and even some other radios these days, where it was 250 to 500 kilohertz LO, and then this was their mechanical resonator filter, which worked pretty well. And now today we're using mostly crystal filters that range from around 3 to 12. 9's very common, 8.63's. I think the Heath kits had some of them had 3.4 megahertz filters. So this looks pretty easy and pretty good, but there is a problem with it. And that is, the big problem is the filter, okay? Filter designs are not perfect. And there's trade-offs in the filter that any designer's got to go through. So there's a question of how much rejection we get, that is how much we get rid of the unwanted sideband, versus the distortion in the filter and the cost of the filter and the amount of loss we have in the filter. So one of the problems is I get a very steep for high amount of rejection, I tend to get more distortion in two ways. One is the response of the filter within the passband, that is the frequencies we want to pass, becomes more erratic and varies. And the second thing is something we call group delay time, which is phase distortion. So what that is, if a signal goes, as a signal goes through a filter, different frequency components actually propagate through the filter at different times or different speeds. So they're, particularly if you're running digital, wideband digital, that becomes a problem, because all of a sudden this symbol and that symbol at different frequencies are not getting through the filter at the same time. And it can actually smear the signals, the symbols that you're trying to get digitally, and cause a loss of errors in your data transmission by not and it's all caused by this group delay issue in your filter. It's also rough on your ears if you're listening to sideband, if you have a lot of phase distortion as well. It's not real apparent at first, but it wears on your ears. So, so there's a trade-off in this. So there's no such thing as a perfect filter. And typically we have a number of families of filters that over the years they've come up with polynomials that describe them. And the sharpest fall off is usually an elliptical or Collier filter design. And these are all just different component values, but it tends to have the worst ripple, and it tends to have absolutely the worst phase distortion or group delay time. Chebyshev filters are quite commonly used, and I think a lot of our filters are Chebyshev because of their roll-off characteristics. They do have some ripple, but you can control that, and you can design a 0.1 dB or a 0.5 dB Chebyshev. So you can, by design, you can limit the amount of ripple in the passband, and then, of course, the less ripple, the less your fall off. So the filter response is not as steep, but again, you still end up with a lot of phase distortion. Butterworth filters, and particularly and then the bezel filters, probably have the lowest amount of distortion, but they also have the worst roll-off, which means to get the signal down the same amount, you need more and more poles in those filters. So filters are not, there are issues and disadvantages with the filter method, and it primarily lies in the characteristics of how you actually build a good filter. So let's get on to this phasing method. Okay, also called the Hartley method apparently, because he's the guy who invented it. I assume the same guy who invented the Hartley oscillator. So single sideband transfers with phasing were kind of common in the 1950s. Central Electronics, the CV100, and a few others used phasing. Hallicrafters had it in their HT37 and HT44, of which I have both. E.F. Johnson's pacemaker, which Mike AE4R has one, is a rig. The Heathkit SB10 was an adapter for single sideband that worked with like the DX100. And also Gonset made a nice little transmitter that was a GSB100. And all those were commercially ham rigs that used phasing. So phasing is still used by homebrewers, and it has some interesting applications today. And some of well, basically, most all of your software-defined radios use a phasing technique. They do it mathematically, maybe in the software, but they are actually using a phasing technique to get to generate the signal, because they can't filter out very well, because in digital filtering you have a problem with side lobes, and it's not as all clean as some people might think it may be. So to generate SSB by the general phasing method, we need to have a couple of signals. We need to have two copies of our modulating signal that are in quadrature. That means they're 90 degrees out of phase with each other. We need to have two copies of our LO that are also local oscillator, that is the carrier generator, if you will, that we're applying to generate the RF signal, that they also have to be in quadrature, which just means 90 degrees. We need two balanced mixers, not one, like we did with the filter rig. And then we just need a network to combine them to. So in the conventional phasing, the amount of unwanted sideband suppression that we get is the function of how accurate is the amplitude balance between the two 90-degree channels and how much they deviate from being ideally 90 degrees out of phase with one another. So a well-adjusted HT37 1950s technology could probably get 40 to 45 dB of unwanted sideband suppression. Today, with the state-of-the-art levels, we're probably around at least 60 dB of sideband suppression, or better. So what's phasing? Okay. So in the phasing method, what I do is I have my audio amplifier, I have my audio processing, maybe a compressor or whatever, and I drive it, split it between in a practical way, between two 45 degrees phase shift networks. So the outputs from here and here are 90 degrees out of phase with one another. Or you can think of this as this is the cosine of our modulating signal, and this is the sine of our signal, because the cosine and sine are basically 90 degrees out of phase. I apply that to the pair of mixers. Okay. And again, the RF I'm feeding into these, our modulating carrier signal, is 90 degrees out of phase with one another. So again, it's a sine term and a cosine. So what I get out of these mixers, this one here, I get the sine of the carrier frequency, which is omega C, and I get times the sine of our modulating frequency. And out of this one down here, I get the cosine of our modulating frequency times the sine of our carrier frequency, okay? So here's the math. Okay. So if you do the math in the law of trigonometry, and this is not calculus, it's just trigonometry, okay, the sum of the two sines will give me 1/2 times the cosine of omega C minus omega M, which is your lower sideband, minus the cosine of omega C plus omega M, which is the upper sideband, right? The output of the other balanced mixer gives me, when I take the cosine times the cosine, gives me 1/2 the cosine of the lower sideband plus, rather than minus, the upper sideband. So when I add these two together, I take this signal and just add it to this one. This plus term, this minus term cancel one another out, right? And I'm left with 2 times 1/2, i.e. 1, of cosine of the lower sideband. So that's how I get the lower sideband, by the phasing method. So if I subtract the outputs instead of adding them, okay, make this one a negative, then the lower sidebands cancel one another out. This becomes a negative, added to a negative, so that's becomes 1, right? So then in that case, we just have the upper sideband left. Now practically, I don't really need to change the output and try to connect them in an adder versus subtractor. What I can do is go back up into my input and swap the input signal. So the audio of one becomes the sine, the other one becomes the cosine. So I can just swap them around, I'll get the opposite sideband if I do that. Okay. So in the old days, how did we do this? Well, they had a 90-degree phase shift was obtained with an RC network that provided about 45 degrees of phase shift in opposite directions, but not all that accurately over the whole 300 hertz to 3 kilohertz band. And for RF, we typically have an LRC network that gave us 45 degrees phase shift one way, 45 the other. And one of the early 50s, a guy by the name of Dome invented a simple audio network with a couple capacitors and resistors that was a relatively decent phase shift for audio. And it was actually sold by B&W as a part number 2Q4 that looked like basically an octal vacuum tube. And I actually have one sitting at home. I should have brought it with me. But so today, how we get this high degree of precision. Well, there's two ways of really getting 90 degrees phase shift over a very wide network very accurately. One is to use a string of op amps in what's called an all-pass network, which is basically like a string of, you might think of them in terms of the way we build low-pass, high-pass, band-pass audio filters. But the RRC values are selected, so basically the frequency response is flat. But what happens is we get a phase shift through it. And you basically, each stage has the phase shift at a different frequency, and when you start cascading them out, you can actually get the two outputs will be 90 degrees out of phase over a very wide bandwidth, and with an accuracy of less than 0.1 degree offset. Polyphase network we'll show you later on in the presentation. That's another newer way of doing an RC network to get 90 degrees phase shift or more. We'll show you that at the end here. The RF phase shift, today, commonly they use a 90-degree hybrid. Via digital circuits, you can use two flip-flops clocked at 4 times your desired output frequency and pull the outputs from the flip-flops, and you get two signals that are precisely 90 degrees out of phase. And there are some DDS chips available that provide precise 90-degree output signals. They're precisely 90 degrees out of phase. So the technology has changed a lot from the 1950s. So you can really actually get a very good. So why do I want to do this? Well, I think you can get lower distortion and cleaner sounding receivers with the phasing method than we can with filters. So there's another third way of generating IF of our sideband. And this is called the Weaver method. It was invented in 1956 by a guy named Donald Weaver. So it gets rid of having to do the 90 degrees phase shift networks by adding an additional set of mixers. Okay? And I have a pictorial here that explains a little bit better. But basically, he takes the first local oscillator and it's put in the middle of the modulation input band. So say if our audio bandwidth going in is 300 to 3200 hertz, he would LO in at 1.6 kilohertz. So we're mixing the audio, and what that kind of does is it actually folds the audio signal back on itself. So when we take the upper and lower sidebands, and they actually fold them back on themselves. And this works, and I'll show you why in a minute. And then the filtered outputs from that are then applied to a different pair of balanced mixers, which are all set by the first LO from the desired output, and we'll show you why that is real quick. And then the outputs are summed, and we get single sideband out. So this is single sideband with no 90 degrees audio phase shift. And by the way, this method is probably used in most digital signal processing radios today to generate their SSB. And the reason is the Hilbert transforms required to do digitally a 90 degrees phase shift on your audio sample stream are a little bit processor intensive. They're also prone to a lot of distortion because of the sampling techniques. And so this is actually preferred over more the direct phasing method for those applications. Okay, so this is how this thing works. We take our audio, feed it in phase to the two mixers, no phase shift network here. We do feed our 1.6 kilohertz LO, okay, at 90 degrees out of phase into the two mixers. I then low pass filter these at 1.6 kilohertz to get rid of everything above the LO frequency. So I'm getting rid of, if you will, my upper sideband. I only have the lower sideband left. I go through again and mix those signals with my desired RF output frequency plus the 1.6 kilohertz LO, and I'll show you why in a minute. And Again, we take that and we put that in quadrature through a 90-degree phase shift network, feed that into the mixers, and out comes single sideband. So another advantage of the Weaver method is that the unwanted sideband suppression is not a function of the amplitude balance between the two channels. We don't have any phase shift accuracy issues. It's strictly a function of how good my low-pass filter is. So in general, you can build a lot better filters, low-pass filters here at the audio, and get better sideband suppression with the Weaver method than with conventional phase modulation. I mean, SSB by the phasing method, let's put it that way. So here's the math. Don't scream, okay? So the bottom line is this is my mixer output, which is basically just the lower sideband and upper sideband. And you notice these are cosine terms. Because I'm feeding the mixer here with a sine wave rather than the cosine wave, 90 degrees out of phase, my output here is the sine of the lower sideband and sine of the upper sideband. So I put them through my filter. Okay, so my filter outputs basically has a cosine of the lower sideband, and I have the sine of the lower sideband. Okay. So the two signals are in quadrature. So I run those through my other mixer, where I mix this with omega 2 and again the cosine and then the sine. So this output gives me basically the upper, let me get these right now. This is the sum, right? Yeah. So I get the sum, I get basically an upper sideband of this cosine signal here, right? Basically my omega 1 minus omega m, modulation with this first LO, and I get the lower sideband, okay, which is this minus this signal here. And again, this one gives me the cosine of the upper sideband here in minus. So again, I can go through the adding network, and when I add subtract these together, just like in the case of the other FM by phasing, the terms will cancel out because we have, again, a minus cosine plus cosine. So if I add them together in this case, I'm left with the upper, let's see here, yeah. I'm left with the upper sideband, and I'm left with the lower sideband if I take the difference between the two. So note that the output frequency of my math here is omega 2 minus omega 1. That is basically, I'm offset by the frequency of this audio LO, which is at 1.6 kilohertz. So I have to compensate my frequency readout by 1.6 kilohertz. So basically this omega 1 minus omega 2 omega 1 term combined there. So that's the Weaver method. So it's not quite as intimidating as it looks at first. So the other thing I want to talk about is commuting mixers. These are relatively new. In the last 20 years they've become popular. And they're kind of interesting in that mixing occurs by switching rather than by normally using what we think of as a diode mixer or transistors. If you could run a switch, mechanical switch fast enough, it would work. And they actually work pretty well. They were done back in the 40s at low frequencies, but as I said, really in the last 20 years. And that's because of the availability of really high-speed switches. Kind of the starting was the CMOS 4066 that's been around since the 1970s, was the first one of these electronic switches, digital switches that basically let you turn on and off an analog channel within the, which was a CMOS device. And now we have, and that one operated around a switching time on the order of microseconds. And now we have devices that switch in times of nanoseconds. So this is a simple little RF mixer. I have built and used this circuit actually. And you can see here, basically all it does, we switch between this point here, which is kind of our neutral, that's tied back to the center tap here. Basically, we just switch between this point and this point, back and forth very rapidly. So what I'm doing is switching from this. So I'm taking this end of the transformer to ground, then this one back and forth, right, to the center tap. And I put in my my switching rates controlled by an LO, which these are just some amplifiers that drive the switch at a really good square wave with really fast rise times to drive it. And I apply my if I use it for a receiver, I can put my RF in here, and the switching will then produce the IF output. And this is actually a double balance mixer, and they actually work very well. So it's a different kind of way of doing switching, okay, for mixing, using a switch as a mixer. So let's apply this to generating single sideband. So what we do is we generate 4 phases of our modulating or audio signal that come out at 0, 90, 180, and 270 degrees. We can do that by a couple things. One of the easiest ways is a Polyphase network, and I'll show you a picture of that. Or we can actually do that also with an all-pass network with a bunch of op amps and resistors and capacitors. So what happens in this technique is that each of our phase of the audio is sampled basically by a switch rotating at the carrier frequency. So this is usually done by applying one of 4 phases of a carrier to a switch that is usually like a quad bus switch IC that samples one of the audio outputs. And I want you to remember, I talked to you earlier that the US we have a lower sideband and upper sideband. The upper sideband is a counterclockwise rotation of the side bands, remember that? And the lower sideband is the clockwise rotation. Okay, so basically what I'm doing here in this commuting mixer scheme is I have my 4 outputs at 0, 90, 80, and 270, and I have the switch rotating, if you will, at the RF frequency that I want to put out. And what it does is samples this one, this one, this one, this one. So and it gives me either USB or it should be a lower sideband, not single sideband. Anyway, so if I want to change from one lower to upper sideband, all I have to do is switch the flip the 0 and 180 here. Okay, and put this output here and this one there, and then basically it'll look like it's rotating the opposite direction. And that's how I switch between upper sideband and lower sideband with this modulator. Well, we'll get to it. So, so this whole mixing scheme is really quite common in receivers for detecting signals. It's used in the soft rock 40s. It was used in the front end of the, it may still be used in the flex radios, this type of a mixer. And I didn't have time to really find a whole lot, but I did pull these off. So this is kind of the receive mode. Basically, you have 2 signals in quadrature that drive the switch, which basically causes it to rotate this way. You put your RF in. You have to bias this, of course, a little bit to get the signal right, the voltage right. And basically, you can drive a pair of op amps in this case, and you get out, your output comes out 0, 90, 180, 270, and you can recover that and get your single sideband, either upper sideband or lower sideband out, because you've got your 2 quadrature signals here. Or we can do it with a polyphase network directly connected to the 4 phases. Okay, the exact opposite happens in the modulator, which we were just talking about. The same thing I was talking about. You take your audio at 0, 90, 180, 270 into the switch. We clock the switch. So these are individual FET switches basically inside the IC. So we clock them 0, 90, so we get 4 states, right? 0, 0, 0, 1, 1, 1, 0, 1. Each one corresponds to the switch being connected to one of these inputs. And then coming out, we have our single sideband. So this is kind of a neat way of doing it, which is relatively new. It's only been around, I think, for about the last 20 years. The guy came up with the idea. And this is what a polyphase network looks like. I was talking about this. So this is a resistor capacitor network that's designed so that I put my differential input in here, not really two separate signals, but one. Like I just put a transformer across here and then feed my audio into it. And it outputs 0, 90, 180, and 270 degrees phase shift signals. And you can go and run them the opposite way back for the receive. And they'll combine them back into a differential pair. So that's what the polyphase network is about. So that's kind of the neat way of generating SSB that is not that widely used yet, but I think is, as I said, it's also something which can be done probably in digital implementations as well. So that's about it. So now, anybody have any questions? Yeah, go ahead.
The historical reasons for why traditionally we do lower sideband on 40 meters and below and upper sideband on 20 meters and above. And I think I know the answer to this.
I'm not an expert on that, but I think the bottom line was we have this neat way of generating using the 9 megahertz crystal filter with the 5 megahertz VFO. And when you did the mixing, you got upper sideband on the upper side, so it was 20 meters, and lower sideband down on the other side. And I think that's kind of where that whole concept came from. But technically, today, there's no real reason why one or the other should be preferred over the other. It's just, yeah, pretty much. Yeah.
There is another story on that, is because the command sets that were available. Right. There were so many command sets that were never used that the 7 to 9 megahertz command sets were available. And I mean, just think about it. You go one way for upper, go the other way for lower from 9 megahertz. It actually was quite easy. There's a story about that in some old not double, but sideband book there a long time ago. That was their argument.
That predates me whenever they decided to do that.
Well, I just want to say thanks to Lee and to, is there another question?
I think Mike wants to make sure everybody has gotten signed up on the
yeah, okay.
sheet
And
there.
to Ron for their help with this. And I want to tell you that I feel like if you listen to this and you paid attention, you all are now awarded master's degrees in electrical engineering. There you go.
Jason?
And do you have questions from the net? So the question was, when was
single sideband?
Sideband first used commercially?
AT&T started using it for some landline stuff about World War I era, but for actual radio, I think 1922 was the earliest that I could find that was used commercially.
Any other questions from the net?
John?
That was it. John has one.
Often you'll hear the term bandwidth, and when it refers in common parlance, it really refers to the information capacity of a channel rather than the actual mechanism.
There's a term called necessary bandwidth, which determines actually how much spectrum you need to transmit a given amount of information using a particular type of modulation. And that's actually fairly well defined in some of the ITU regulations. And I know in the government, when you need, well, as part of the whole emission designation system for, what kind of transmission you're putting out, you have to actually specify your necessary bandwidth that's required to transmit that information over that channel. There really isn't a technical answer to that.
By the amount they cringe when they hear bandwidth misused.
We have a time problem here, so thank you, Lee. And again, one of the things I love about this club is it's very social. So I know there's going to be some social time here, but we need to clear the building by 9:30. And if you have moved a table, please put it back where it was. And some people might feel like helping KM4JOA Kurt move those tables back in here. So thanks a lot. Next meeting is in 2 weeks, the 8th of March. It'll be right here. It'll probably be in the cafeteria, not in this room.